So yesterday we had two lectures on introduction to the transportation geotechniques, climate resilient transportation geotechniques, the need for such a concept, and also we had a discussion on the state variables. We discussed that state variables are the dependent variable in the governing equations, fundamental equations. So that's how the void ratio, stress, all of them are the state variables. So this is coming from a continuum mechanics concept. So then we discussed suction could be the ideal state variable representing unsaturated soil behavior. Of course, the moisture content is also one of the state variables. Now, these two state variables constitute a relationship. Changes in the suction with moisture content is one of the important constitutive relationship that we need to develop. And we had a lab session yesterday. So in the lab session, there was some discussion on the measurement techniques. Although we could not give the background to some of the measurement techniques for these state variables, I'll try to do that today after describing the constitutive relationship. So yesterday it was said that the suction is nothing but soil water potential, which is a combination of matrix potential, osmotic potential, and adsorptive forces all put together. It constitutes a matrix suction. When salts are present in water, again the potential is dropping, which is contributing to osmotic suction, which is slightly different from osmotic potential what we described in matrix suction. Nevertheless, put together, you have called something called total suction. Total suction is a positive quantity. How much is the potential drop with respect to atmospheric conditions? Atmospheric pressure, you may have 101.325 kilopascal air pressure. So with respect to that, how much it got dropped, that is what it is describing. So in terms of head, it may be negative, but when we describe in terms of suction, which is UA minus UW, therefore it is a positive term. So that's how in geotechnical engineering we adopt. So in generally water resource and other soil science areas, they use suction head or soil water potential in negative sign, but we use suction in positive sign because it is with respect to UA. So therefore which is used in positive term. There are some advantages when you are using some empirical models using UA minus UW concept or suction concept. So I will try to describe more about this suction so that we will be very familiar with what suction and what we are talking about. If I take a capillary which is completely filled with water, and if I have a capillary which is open both sides, if I just keep it in hand, water will not drop out because capillary is very tiny and the surface tension which is acting inside, or the potential drop because of which the water is actually existing inside, which will act against the gravity, so it will not fall off. Even if you take a thin capillary which is given for stirring your coffee, right, after the capillary rays, if you take out, it will not drop out unless until you tap it, right? So it is actually acting against the gravity. So that is the condition in the first case. If you give some energy or try to suck the water from it, right? So what happens exactly is that it seems water will not be sucked out immediately. It tries to bend, it tries to become curved, right? It's called receding angle. It is kind of becoming like this in the second picture. Slight water content might decrease, but it is fully saturated because air hasn't entered in it. Only the meniscus angle got changed. So further if you try to draw, then it may have to give up and then start dropping. So which is where the water is getting replaced with air. So why in the second and third cases only angle is getting changed but not water is dropping down? That is because it has some interactions, right? Adhesive interaction between surface of the capillary tube and water molecules. So because of which it doesn't want to get out of the capillary. So it still has, he's trying to hold the capillary tube inside, and but still, because you are giving some energy, some part of it is actually getting evaporated. That is what is happening, right? So what does it mean? If I try to represent in terms of a graph with respect to suction, on x-axis, suction on x-axis or negative pressure, right? I'm trying to decrease the potential. Therefore, suction is what I'm trying to decrease the potential inside it. So therefore, water is coming out, right? So when I'm doing this should happen on both sides, in fact. Okay. So that is how it should happen. So water is actually coming out, and here the air entry started into the capillary tube. So if I try to draw the volume of water present in a tube with respect to negative pressure, this is how it represents. It tries to drop like this, but at this point it suddenly drops because air has entered here, right? This is how it represents. This is what with one simple capillary I'm showing you, right? Yeah, sorry. If I do that with several capillaries attached together, something like this, a bigger capillary with a bigger radius and capillary with the smallest one, and in between you have a number of these things, right? Again, now this particular capillary network got completely filled with water in the beginning, and I'm trying to draw water. So water will be dropped from the largest pore first, correct? Largest pore has lower potential, so water will be dropped from this. So if I do that, if I continue the same thing, water will be dropped here, and then slowly even thinner tubes will give up, right? So in fact, our soil pore network can be can represent or can be mimicked by this kind of a simplified structure, which will be much complex, of course, where you have number of pores connected at any given cross section. So that could be described with a number of capillaries attached to each other at a given section, cross section. So now, if this can be plotted on x-axis, you have a negative pressure, negative pore water pressure. On a y-axis, you have volume of water or volumetric water content, we say, which is volume of water by total volume. So we are accustomed to use gravimetric water content, which is mass of water by mass of solids, but in unsaturated soil mechanics, we use volumetric water content for a reason which I'll describe after some time. This is volume of water by total volume, right? So if this happens, the curve looks something like this, where initial drop in one of the capillaries that happen like this, and next smaller one, smaller to the largest pore, that actually drops here, and the finest pore gives up at somewhere. If you combine this, you will get a interesting relationship, kind of a S curve, which is called soil water characteristic curve or water retention curve. So this is exactly what happens when soil mass, saturated soil mass, is exposed to some atmospheric conditions. That's what we do in shrinkage tests, right? In shrinkage tests, we try to mix the soil with water and keep it in the atmospheric conditions under some RH and temperature. Then evaporation takes place. Why evaporation takes place? Why evaporation has to take place? Because the vapor pressure difference or the energy difference. in the last class I mentioned about Kelvin's equation, which relates RH, temperature, and suction. You can understand what suction are the potential which is available in the atmosphere. We know the RH, we know the temperature, we can evaluate. So that is a suction in the atmospheric conditions. And you have a saturated soil mass where soil water potential is 0, right? So there is a difference in the potential. Therefore, there is an evaporation that is taking place. It is giving away water. If a dry soil mass from oven dried, after cooling down, if you keep it outside, it tries to absorb moisture from the atmosphere because there is a potential difference that it is trying to equilibrate with, right? So there is an exchange of mass that is taking place because there is to balance the energy, right? Same thing is happening, I'm not sucking literally, but evaporation is taking place, so therefore this is what is happening. So this relationship describes how fast the pores are giving up, or how large the pores are inside, or how small the pores are, and how the geometry is actually existing. Because previously, if you see, there is only single capillary. If I can make a material with symmetric pores of same size, the relation should look like what it was like this. Like in case of filter paper, you may have uniform pores or porous discs. They may have a relation something like this. But in case of soils, any heterogeneous material having heterogeneous pores all across distributed, you may have a relation something like this, right? S curve. Your particle size distribution curve, any curves you take in soil mechanics, they follow the same trend. So essentially, even effective stress versus void ratio, the relationship looks similar, right? In effective stress versus void ratio in a consolidation test, you are applying a pressure and volume is getting compressed, right? So you are representing void ratio with respect to effective stress. Here also volume might get changed if it is an expansive soil and evaporation is taking place, so suction is there. Both can be plotted together, but both represent S curves, but they differ. That maybe we will discuss later on, right? So there you are applying a mechanical pressure, here we are applying force, which is suction, right? So that is the difference. Now, if I have a soil column, so it's a more realistic, right? The soil column which is placed in a water reservoir. So what happens? Water anyways would be there up to this level, but then beyond that there is a capillary raise that takes place, and there is a capillary raise, and maybe this is the point where there is a section where all pores are below that, all pores are fully saturated, right? Above that they may not be, because you may have different capillaries attached to individual sections. Beyond that, maybe a larger pore is getting exposed and air is entering into it. Thinner pores still they are saturated. So combination put together, this is partly saturated. Some pores are fully saturated, fully filled with water. Some pores are emptied by air. Therefore, at any cross section beyond this, soil is partly saturated, right? So what is this called? Capillary raise and air entry head we can call. So beyond that, air is entering into your system. Until then there is no air. You cannot see individual capillaries separately here. Here soil means together, right? All capillaries put together. Just like in the previous illustration where number of capillaries are attached to each other. Similarly here capillaries are attached. So therefore beyond this, soil, within the soil pores, air has entered. So which is called air entry suction. Or this particular height is called air entry suction head or capillary raise simply. Beyond that, capillary fringes are there. Partly it is saturated because thinner pores might have received more water, and that's how they are. And after very long distance from this or height, you may see that it may be completely dried also, depending on the type of soil, right? And this process also is a time-taking process. It is not instantaneous because it depends on hydraulic characteristics, permeability or the hydraulic conductivity, how fast they can go up, right? So if I describe the soil water characteristic curve, so this is UM minus UW, right? So how much water pressure has dropped or potential dropped against a reference potential, reference pressure, that is air, that is UA minus UW, which is a positive value. We give a sign something like this, psi, suction, which is representing suction in kilopascal only. Generally, E versus log P in logarithmic form we represent because the ranges are too high, right? So we also represent in terms of in logarithmic scale. Okay, these are in logarithmic. Okay, so this is in logarithmic, and this is theta, which is volume of water by total volume, right? So the curve may represent something like this. So theoretically I'm just plotting, but you may have a number of data points when you do an experiment and measure it, right? So often, this is thought that this is the air entry value, or for a better understanding the air entry value, you should represent in terms of degree of saturation. So there is a relation between theta and degree of saturation. We can convert because anyways the density is known. In fact, there was a question yesterday also. You can always convert gravimetric water current to volumetric water current to degree of saturation if you know the volume of the soil mass. So volume of the soil mass has to be known. Density, ρ, dry density should be known. So then we can convert from W to theta, and from degree of saturation everything can be done, right? So because void ratio is required for that, so ρ is required and we can convert easily. That's how we obtain in terms of degree of saturation or in terms of volumetric water content. So degree of saturation, it represents something like this, because until here soil is fully saturated and then air has entered here, which we call air entry value or air entry suction value, and after that larger pores are giving up, and then thinner pores are giving up somewhere here. Again you have another bend which we call residual water content somewhere here, and after that the decrease is very negligible because thinner pores are getting emptied over here. Their contribution is less in the total mass of water. In total volume of water, their contribution is less here, right? Because only thin, very tiny pores are present here, are still saturated or maybe partly saturated, and they are giving up the water here. So the contribution is very less. If you change a suction from here to here, the change in the water content is very small, tiny. But for the same change in the suction here, it's a huge variation in the water content or degree of saturation, right? So this is a very important constitutive relationship, which is a backbone for understanding many concepts, many engineering concepts like shear strength variations, hydraulic characteristics, volume change, anything you talk which is directly is influenced by soil water characteristic curve, or we can in fact correlate different characteristics using the SWCC or WRC, whatever it is. So in general, the air entry of sands is around 2 kilopascal. Okay, so beyond that it quickly desaturates, and for silts 100 kilopascal. It's a kind of a rough estimation. It's not a accurate values for a given soil. You may have a uniform sand or well graded sands, etc., right? So In that case, SP, all those things, things will change. Obviously, SP will have slightly less compared to well graded. Right? Well graded, it will have pores of smaller size as well, right? So it will try to take you to larger air intersuction values. So silts generally around 100 kilopascal or so, and the clays can vary to even MPa, megapascals, right? So theoretically, how much it can go to, how much maximum suction can exist? There was a theoretical work given by Fredland. He mentions that it can go to 1000 MPa theoretically from thermodynamic perspective. So 10 power 6 kilopascals, sorry. It can go to 1000 MPa, it seems. Okay. So we don't require up to even 1000 MPa for even bendonites. Even 20, that around 80 MPa or 90 MPa almost will come to here. So we can guess what will happen, right? So I was trying to describe in a natural system, you have a ground surface here and groundwater table here. This is the groundwater table, this is the ground surface. Right? Now there is a capillary raise. Capillary saturation takes place. Capillary saturation takes place, and this is a capillary raise. And beyond that, this is how it changes. Even SWCs can be drawn here. So this is the suction because there is a negative pressure. Here the potential is 0, correct? So beyond that, it's a negative pressure, negative potential. So water content changes in this manner. So this is a theta S, saturated volumetric water content, and which almost is constant, slightly might decrease. So beyond that it starts decreasing because area has entered here, right? Up to here it is fully saturated. Remember, although this is fully saturated, there is a suction, right? So there is a negative pressure in this. Just like when you take a beaker of water and insert a capillary in it, so you have a capillary raise. So this is the water in the capillary. So this is a point where you have the zero potential and the potential is decreasing continuously, right? So within this capillary, the water potential is negative, suction is negative, but it is fully saturated. There is no doubt about it. There is no air in it, right? So that is what we are talking about here. Although within the capillary raise or up to this particular height, the soil is fully saturated, there is a negative pressure or suction within it. So this is what I was describing, and in the previous case I was describing a drying phenomena, right? There's a drying phenomena that is taking place where I was trying to suck the water from the initially saturated conditions. But here, although a similar concept was described, but here initially the soil was dry and it got wet because of the capillary raise here. So this is a wetting phenomena that is describing. For the same soil, we can obtain the relation between suction and volumetric water content through drying process and through wetting process. Interestingly, they both differ quantitatively for the same soil. That means it has a hysteresis, right? Hysteretic effect is there on soil water characteristic, the suction versus degree of saturation or theta or whatever, right? So that is because of number of reasons. So I don't know whether I'll get that much time to describe today. So this is what I was telling. There are some characteristics like this is the air entry value, this is a residual water content, right? So this is the condition of the soil at different states. This is a saturated state and this is the residual state. Residual state, thin water film is present around the soil system, or any thin pores are there, water might be there. So that is the condition it is in. So for different soils, the soil water characteristic might vary in this manner. So for example, one particular section if you take, sand completely got desaturated for this section, clays still fully saturated for the same section, right? So air entry is differing, you know, for each soil, somewhere here. So for the same section, clays would have been fully saturated, sands would be fully dry, right? So suction is the one which plays a role, because that is what is the energy, that is what is the potential, right? So if you bring two soils together, the exchange of mass depends on the potential of individual things. Yesterday there was a discussion with Bhargav. Plants, you know, wilting point of the plants. You know, plants have certain capacity to draw water. So if the capacity of the soils for holding the water is exceeding the capacity of plants to draw the water, then they wilt. Because in black cotton soil or expansive soil, most of the plants would not survive because of the same reason, because they have higher potential. So they will not give up water that easily. So if you plant something which will not be able to take the water because of the suction difference, you know, this has a very strong potential, it will not give up the water. If you keep these two things together, sand and clay, obviously clay will take the entire water, sand will get dried, right? So this is the drying wetting curves. Wetting curve, for the same suction, water current will be less all any given time. So this is the initial drying and initial wetting, and then you will have a hysteresis curves, loops, okay? So there are a number of reasons why you have hysteresis. One is because of the pore network, and we also call in-bottle hysteresis. And for the non-curved surfaces, like which is very common for in soils, the relationship earlier 2Ts by R gets converted to this particular form. And from there, you know, how the estimation can be done, can be, you know, understood theoretically. Theoretically, you have some models which are for ideal conditions, highly ideal conditions. These equations are available, these models are available for estimation of SWCC. Because I wanted to actually describe simplified methods for evaluating the SWCC, right? So there is also part of the syllabus that has been given. So here these are some of the models which can be evaluated for idealized cases. I just simply give these slides to you, but you can get back to me if you have any questions. But these are too theoretical, they will not match with realistic soils. So I generally teach this to build a theoretical understanding how to bring a model, right? So I'll actually describe one particular model which is called Arya-Paris method. Arya-Paris method is around 1981 or 80 this was given. From the particle size distribution curves, we can evaluate how the SWCs can look like. Qualitatively they are amazing, they can represent SWC variations very well, but quantitatively there may be slight difference that might happen. There is one single model parameter in a small range. If you use that, you can predict the SWCC. So essentially Arya-Paris method is based on the grain size distribution curve. Both are S curves, interestingly, the particle size distribution as well as SWCC, right? So from here we are trying to predict the soil water characteristic curve. So why SWC is required? You know, we are having many participants from industry. In landslides, for example, if you want to understand how the failure is happening, first and foremost thing, I think we should have SWCC, right? Because when the wetting takes place, how the suction is changing. From the suction, you can evaluate how the shear strength is changing. So when shear strength is changing, the factor of safety itself changes. We actually evaluate temporal variation of factor of safety with incessant rainfall, with a continuous rainfall which takes place. Using several evaporation infiltration models, we evaluate how the shear strength is changing within the soil mass. Based on that, we evaluate the factor of safeties. Factor of safety is now a time dependent thing with change in the moisture content. So we can in fact predict when the landslide is going to take place. We have done that study in fact for Shillong Nihu site previously, which is published. Right, so these predictions are possible. These are physics-based predictions. They are possible once we have a good understanding, solid understanding, and soil water characteristic curve. Secondly, the flow characteristics. When the flow takes place, infiltration takes place into the ground, or evaporation takes place, you require drying, wetting SWCCs. Without that, it is not possible, right? So the flow characteristics can be understood using this itself. So that's why understanding for a given soil, these characteristics are important. So the grain size distribution curve, if you have, we make number of segments. So this is a segment 1 to say n number of segments. If you make more finer segments, it will be more accurate, right? So from these segments, we have certain relationships like determination of void ratio. Void ratio from the dry density you can determine. This is the GS, specific gravity, or the density of solids. From the specific gravity you will get the ρs, and this is the dry density. Knowing the void ratio, you will get the dry density, right? So having that, or MS by total volume, that way also you can determine. So then you can determine the pore volume for individual pores, individual segments. So I segment, the pore volume can be determined using this. So this is the percentage finer calculation from n plus 1th segment to nth segment. So based on the void ratio and ρs input, you can determine pore volume for individual segment. And the volumetric water content can be determined by this one divided by the bulk volume, that is 1 over the ρd, and summation of those things, right? So this way you are actually joining all the pores, initially starting with one particular pore. It's a accumulation of all different pores. That way you will get the theta, volumetric water content. And similarly, pore radius can be determined using this, where you have the volume of the radius. Radius is considered to be, pore radius is considered to be spherical. Based on that particular assumption, this equation has been given, and void ratio is there, and n can be determined from this, assuming that it's a pore is a spherical pore, and using that you can determine the pore radius, and substituting the pore radius in the suction head calculation, you will get the suction. So in this you require cos beta, which is a angle, contact angle, and with that you will get the h value, head. So for a given pore, you can determine the suction head and you can determine the pore volume. So the tutorial is not present for this, but tomorrow onwards, in the second half, you get a good time. So please do try this, because the slides will be given today. Already the printing is, for the printing these slides have been given. So we are available any afternoons. So please do come back and do solve this. This is very interesting, and you can in fact try to qualitatively understand how the SWCs can change for different soils. So this is how the values change, and so this is the measured data, and close prediction is possible. So we predicted these things for different parameters, alpha values. Alpha values do not change significantly. So small variation, this is how the predictions can be possible. So we also did for different type of soils, starting from well-graded soils to gap-graded soils. This is how the particle size distributions vary, and for the same thing, this is how the soil water characteristic curves change. So if you have a uniform soil something like this, right? Look at the corresponding soil water characteristic curve. So for the uniform soil, uniform coarse grained soil, this is how the SWC is varying. So this is the air entry value, right? Air entry is less, around 1 kilopascal for the coarse grained soils, and quickly it desaturates. By 10 kilopascal, it is completely desaturated. Correct? If you take uniform fine grained soils, the suction may be, air entry suction may be increasing, but desaturation is quick. Well graded soils, this is a well graded soil. So look at how the SWC is varying. It is going up to nearly 50 MPa, right? That is getting desaturated there. So there's a beautiful relationship between particle size distribution and soil water characteristic curve. There are a number of assumptions made in this, right? Still, a very good qualitative representation of SWC is possible. There are a number of models developed even after this. But this is a first of its kind where relation between these two have been drawn, right? So this is the equation representing transient flow behavior in partly saturated soils. I think Professor Claudia will be describing these Richard's expression. I don't want to derive or describe these models, but I just want to actually inform that there are state variables or dependent variables if you see in this expression. One is matrix suction head or suction, other one is hydraulic conductivity and matrix suction. So these two are required to be determined. Moreover, they are in functional form. K is a function of hydraulic conductivity is no longer a constant value as we do it for saturated system, as it is partly saturated soils which is dependent on matrix suction head or suction. Similarly, HM is also dependent on something else, right? HM is also dependent on something else, right? That is theta. So the variation of HM with respect to theta is nothing but soil water characteristic curve, suction versus theta. That's what we've been describing so far. So this is hydraulic conductivity variation with respect to either suction or volumetric water content. So these two constituted relationships are paramount important for evaluating the suction head or suction variation with respect to space and time in transient conditions, and R theta variation with respect to space and time, right? So for example, there is a flow that is taking place against the gravity here. How much time it takes to understand or at any given time how this profile is changing. This is with time t1, t2, t3, right? With time the profile itself is changing. So this may be the capillary rays in the beginning, this is the capillary rays in the beginning, then this is the capillary rays, this is the capillary rays, finally this is the final capillary rays, and this is how the transient flow is taking place. This can be understood, the spatial variation of theta or suction, using this particular expression. This is a transient expression called Richard's equation. Very old, 1911, but still it is in use. Fine. This again uses mass conservation of mass expression here. So now, as the SWCC was already described, and the hydraulic conductivity function is important, and Professor Claudia will be describing how to evaluate the K values in her next lecture. So I will not describe very detailed about this, right? So I'll just skip in case if it is required. I'll come back whenever we have some time in the afternoons. So there are three things that we have to determine. One is soil water characteristic curve, RWRC, water retention curve, hydraulic conductivity function that Professor Claudia will be describing, and volumetric shrinkage curve. Right? Yesterday also there was a question in SWCC. Some of the methods that were described, they mostly are like measuring or are estimating or controlling the suction, either total suction or metric suction, right? And you also try to estimate the water content by weighing methods. How to get volumetric water content or SWC is where most of the software take the inputs of soil water characteristic curve in terms of volumetric water content versus suction. So to do that, like a GeoStudio or Plaxis or anywhere, Plaxis recently it started taking. So to do that, we need to have a volumetric shrinkage curve, which describes the relation between theta and W. For this, dry density has to be estimated, volume, mass of solids per total volume. Volume is required here. So you evaluate the volumetric shrinkage curve also. You know that shrinkage which happens, so this is gravimetric water content, this is volume of the soil sample, right? So generally we draw like this, correct? We say that this is the shrinkage limit. Correct? This may be true for sandy soils or something where you don't require the shrinkage, coarse grained soils. But actual curve varies something like this. Okay? So the actual curve describes something like this. So this is 1:1. This is how the slope is changing. So the desaturation starts somewhere here. The desaturation starts somewhere here. Right? Constant volume happens somewhere here. So a huge difference in the water content range before it desaturates, before it starts changing from the saturated conditions, and after it started becoming the unsaturated part, and before it becomes constant volume. So generally know that these 2 points are the same, right? But it doesn't happen. So there are a number of ways to evaluate the volumetric shrinkage curve, and water content anyways we estimate using gamma ray and time domain reflectometry, TDR, and these sensors we commonly use, and these sensors will be described today afternoon because we will be using them. They are very, very handy in using in the field. Quickly they can give the volumetric water content itself. So volumetric shrinkage curve, there are a number of ways to determine because we require the entire curve. Generally, mercury displacement is no longer in use. In international community, people don't use. Unfortunately, in Indian standard codes, still mercury displacement is still used, but then it is not used anywhere. Okay, so individual soil sample you take and then you immerse and do it, right? So that is no longer useful. We require the entire curve. For that, we use number of methods, maybe shrinkage box, but if you use highly expansive clay acidic curve, and determining the volume is very, very difficult. So simply by measuring the volume, width, etc. is not possible. So wax coating is one method we commonly use, because in the field also we use, right? Field sample has to be brought to the laboratory. We use a wax coating. So look at the consistency. At this consistency, definitely you can't do the wax coating, because it should have good consistency where you can hold the sample and coat it. You put it in a hot molten wax. For that, you require good consistency. So you will be missing some points here. So somewhere here you will start, right? Hopefully that is before the desaturation starts. Otherwise you will be missing few points. And balloon method is one method which we also try to use, and which has some positive points, but it also deviated for some cases where you use a larger balloon volume is not considered, and also there's a air which is actually is stuck here, and it requires a good contact between balloon and soil sample. Often that cannot be placed in the field in the laboratory. So right, so we have also used clot tests where we started coating with respect to PVA glue, and therefore the glue, once it dries, it allows only air movement, and water will not go inside. So therefore if you immerse it in directly in water to measure its change in the volume, water will not enter into the soil, so that soil will not get wet. After that, if you take it out and then keep it outside, it will get dried. So intermittently I can take the soil sample which is coated with PVA glue, I can put it in the water and measure its volume, take out and then keep it in the outside. So continuously water content will be decreasing, volume also will be decreasing. There is a thin film which is protecting water to enter into this. So we found that this is a very good method, and I think the comparison between different methods is shown towards the end, and these are some of the suction measurement methods. I think I'll not mint up her time, so maybe in the afternoon we'll have discussion around 2:30, and we'll have around a half an hour discussion on these methods, and after that we'll go to the field for measuring. Okay, so afternoon lab will be somewhere here only, we don't need to go to the lab. So if you have any questions, I'll take the questions, and these methods I will describe afternoon before we go for the field visit or field measurement. If you are drying a soil mass, air should enter to your soil system or pore system. At what point it is able to enter is described by the air entry. Where exactly the desaturation starts? Actually, we call water entry, air entry, the different points are there. In our drying system, we call air entry. Okay, if your fully saturated system is there, and when you are drying the soil sample, where exactly air enters into the largest pore of the system. Largest pore of the system is called air entry value.
And water will enter in the smallest pore if we are wetting.
Yes.
That the wetting and drying both the curve will be different. Now again I have to re-wet the same curve. Will it be same or
it will be in between? So there is a loop which I showed. So you have a drying and wetting, right? So it will go in between. It will follow hysteresis, right? So it will be in between the loop. It's called secondary wetting, secondary drying, all these things. Yes, yes, yes. Yeah.
The method based saturation is done with late humidity method. Sample absorbs the moisture that is there.
Can we use the microphone for that?
Yeah, true. You change the mic otherwise.
So conceptually, can I use a small volume humidity chamber where I keep the dry sample and I set a humidity value? Where I directly know the humidity, and then after some duration I take out the sample and estimate the water content. So will I be able to plot the curve?
Yes.
So is it logical?
It is, of course. This is one of the methods we use. The vapor equilibrium method is exactly doing the same. Instead of using salts, you are controlling artificially using humidity chamber.
Correct.
You are controlling the humidity at different points. So you set say 100, 100 RH or 99
95.
RH, then maybe 95, 96 RH or 90 RH, like that you are setting.
Correct.
And you are exposing the different soil samples to these RH conditions by maintaining constant temperatures, and at equilibrium you are measuring the weight. That is one
Yes.
of the methods we use.
Yes.
But now the question is, if you have expansive soils, how do you control its volume? Because the volume also changes, right? If it is expansive soil, like you are going for a wetting path, then how do you do it? Like it may come out, or
Swell.
how the swelling takes place, and it takes very long time. These are very long time, very a long duration process. Each method for one particular RH, if you are controlling, it takes nearly months to come to equilibrium for one single point, right? So there are a number of methods they are available. In fact, we could estimate for compacted bentonite. Powder bentonite also we did compacted bentonite of different quality, where the specific surface area went up to nearly 600-700 meter square per gram. For those clays in a compacted system up to 1.7 gram per centimeter cube dry density, we estimated the entire SWCC curves using different techniques, osmotic and vapor equilibrium, etc. Vapor equilibrium takes really long time. So lithium chloride, if you use around what 15 or 10 MPa, sorry 10 RH, I think I showed yesterday, right? K2SO4, lithium chloride, etc. So around 11 kilopascal, 11 RH or something, which can exhibit around 80 MPa or so. We went up to that.
Sir, another question that I have, from the payment point of view, both the subgrade and granular layer. So even South African guidelines and MEPDG US based. So they mostly have like plastic deformation model. It takes into account of degree of saturation as a function. So if for an like it is not established for if it has to be done for Indian context, how should that a function of degree of saturation?
Degree of saturation is function of what?
Sorry, there is a like the equation follows a function of saturation. That model form is not
No, is it a modulus or what? What is it that which is function of saturation?
modulus. Yes.
Modulus, Brazilian modulus.
Right.
Okay, that should be describing. I think
Okay.
she'll be talking about it.
Okay.
Yeah. Yeah.
That's it. Thank you.
Anything else? I think there's a tea break. We'll have. Sorry. Yeah, please.
Drying and wetting, so why is that difference when you come? What are the reasons?
First of all, the contact angle itself is hysteresis, which follows hysteresis. So during drying and wetting, you have different contact angles for soils. Okay, that is one reason. Another reason is capillary hysteresis. If you have a larger pore and smaller pore, which are both are connected, so the during raise it will stop here, and during drying it will be up to here. So that is the reason more water in the drying for the same suction and less water in the wetting. So this is a capillary hysteresis. It's called capillary. What is it? What is it called? Ink bottle hysteresis. Ink bottle hysteresis. So ink bottle, when you are trying to squeeze out the fluid from the capillary, so that time if you just leave it against the gravity, it stops at above the neck, right? But if you just try to take in the fluid, it will stop at here. That is because of the suction difference that is actually existing between two different pores. That most of the pore network within the soil mass is connected by number of different pores, right? So that is how it is described. So generally the contact angle varies within the soil mass. It can vary to even 60 degrees to even more than 90, depending on the wetting or drying conditions. So that's the reason the contact hysteresis is existing in SWCC. Right. So we'll have a tea break, and tea is served outside in the lounge. So we'll come back and assemble here by 11:30.